Okay, everybody, good morning. My name is Julian Pienaar. On behalf of the CBASA, we welcome you today to this webinar. And yeah, we're going to be going through a couple of things about trouble at the taps. Our speaker today probably doesn't need any introduction, but I'm going to do it anyway. With me today is Danie Odendaal. He's a biochemist, a master brewer, and a beer industry expert. With over 23 years experience, Danie has worked in various breweries and in different roles. He has, however, always gravitated to the hands-on experience in these types of roles. Danie has a vast knowledge of experience in the different roles in a commercial brewery, spending almost 14 years in a production environment. The rest of the time he has spent on innovation, problem solving, raw material, and new product development sphere. Danie is a practical problem solver and has been involved in various solutions and driven projects. Danie is a trained technical taster with a ROXA, as well as accredited UJCP judge. Danie is currently heading up his own consultancy in the terms of Bearded Brew. Bearded Brew supplies consultancy expertise in the FMCG environment, focusing on the craft brewing related industries. Welcome, Danie, and we're going to hand it over to you. Thank you very much. Okay, Danie, you can unmute yourself.
Mute myself now. Okay, excellent. Good morning, ladies and gentlemen. Thank you very much for this opportunity, and thank you for having me as part of this Sabasa talk. I think today, ladies and gentlemen, I'm not going to talk about the classic don't do this, and you know a straight list of issues. This give that. I'm going to give you guys a little bit of background around one of the things that I think is some of the biggest issue that you get on draft beer, but also pulling it back a little bit to the brewery specifically, because they also have a part to play in draft beer. So let's start. Let me just get one too many. All right. So guys, when we look at draft beer, we've got kind of one of three scenarios. Generally, we want to give the customer a beer that's well carbonated, or if it's the style that's required, and with at least like a centimeter of foam on top, or some foam on top. But what we see a lot is kind of in this side, where either the beer is well overcarbonated, it's problematic at pouring, and then I have seen quite a few times, kind of stuff that's undercarbonated from where it should be if it is served. So our goal is essentially to pour the customer's beer, right, in a nice clean glass, and in the process maintaining its CO2 content. And I'm talking about maintaining it from what the brewer entailed, what he wanted the beer to be at, and not pick up CO2. And it's so easy with a draft setup to actually do that and then pick up problems. So, so generally, there's a whole bunch of stuff that that is important to make sure that the beer quality is preserved, but also the retailer or the publican's economics is preserved. So you would have seen many times when the guys are pouring the beer, the beer is flowing in and the foam is running out the side of the glass. So that is beer loss or loss of income for us. And if your keg constantly does this, every time I put a keg on, eventually the publican is going to say, listen, your beer, I'm not so sure if we want it. We lose money on it all the time. So generally what happens is that the brewer supplies a keg, we've got the setup, and then we go hold thumbs and we go, yes, let's hope it pours okay. And then, you'd hear people say, this batch, was pouring rough, or this keg is worse than the other one. So what I'm going to talk about today is some of the key steps that is important in serving draft beer correctly, right? And it starts as far back as supplying the keg. So how the brewer, what he did. one of the big things that we need to understand is Henry's law, right? And the impact it has on the draft process, but also in the brewery itself. And I think for a lot of people, when I speak to people, I can pick up that people don't understand what Henry's law does and what the impact is on serving beer. We generally go on luck and that's it. The other thing I'm going to touch on is just about clean glasses. And then, the classic thing about cleaning the draft system. I think people under clean draft systems, and then you constantly have quality issues on the keg. All right. So typically for us for setup, generally there's 3 types of systems. There's the cold plate or temporary systems, which is essentially the jockey box or setup, maybe for the home brewer. But generally tap rooms don't have this setup, but I've seen many that does have it. Generally, I think the biggest one, the most setups that come in the craft kind of arena is the under counter or kegerator setups. And then generally for the bigger operations and big tap rooms, they then have a cold room with long lines. And each one of these things require a gas that forms 2 functions. One is the driving the beer out of the keg, but also the amount of gas and the pressure that it's set at is there to actually keep the CO2 constant in the keg until that keg is empty. And generally the gas that's used is carbon dioxide, CO2, mixed gas, which is normally nitrogen and CO2 mix. And then for the very long line systems, you have to use pumps to push up the pressure in the line without putting gas on. And I'll explain a little bit about why you can't just put very high pressures on the keg to make sure that you're out the front. So just some terms to come to terms with, right? In generally in South Africa, people, when I talk about CO2, they're talking about 2.5 volumes of CO2. And it's kind of a bit of an imperial kind of standard and not metric. Metric, they generally talk about grams per liter of CO2. So Europe and that, they generally refer to this. The US is volume. We're generally volumes. And what that means, when somebody tells you, I've got a liter of beer and it's at 2.5 volumes of CO2, that means there's 2.5 liters of CO2 in gas form that's been dissolved in the 1 liter of beer. All right. So there's a lot of gas that's in beer, and what that as the result is that gas wants to come out of solution. All right. And setups is designed to keep that in solution and to prevent it from breaking out until it gets into the consumer's glass. So general setup, if we look at a draft setup, you have your gas bottle, you have your primary regulator. Lots of times the primary regulator also drives the keg straight, but in lots of setups there is a secondary regulator. So you have a regulating feed at say 2 bar, and then you step it down to 1 bar or 1.2, whatever you need it. The beer is pushed out of the keg. Quite a few of the biggest setups have fob detectors, all right? And a fob detector, essentially what it does is when the keg goes empty, there's a little ball in a fob detector that then drops down if there's no liquid in it, and it prevents you from losing all this beer. You know that when a keg runs empty and you don't have a fob detector in, when you put the next keg on, you have to run it for quite a while, and there's a bit of beer waste that happens. And what the fob detector does is it almost makes that process seamless. Because once the beer is in here, the foam gets in here, the ball blocks the outlet, so this is then solid beer. And then when you put the new keg on, you just drain a little bit here to get the foam out, and then the ball goes back up, and it's then a seamless process, and you can keep pouring all the way through. Then you typically have a chiller that cools the beer down, and then the line going up to the tap. Here in South Africa, most of us use a regulated tap, a flow control tap. where in the US, where I think this picture is from one of their drawings, there is a back pressure control in line. But generally, we go straight here and we do back pressure or flow control via tap. So that's the basic layout of a draft system. And it's important because later on, when we talk about the impacts of pressure and temperature, I'm going to refer back to this drawing for you. So generally, I thought, because we've got quite a mixed group of people here, just to, you know, the brewers would have taken these things apart and they know it quite well, but maybe a few barmen and that don't know what the inside of the keg actually looks like. So generally, the kegs that we deal with is the G-type, but you can get the Sand key, the S, but generally most of the kegs we deal with is the G-type keg. And this is the coupler that goes onto, this is the keg fitting, and the coupler goes onto that. And if you look at it in an exploded view, essentially it has the central shaft. So the beer comes through the central shaft, through the coupler itself, because this, remember, this is actually inside here. And then you have what they call this torpedo or ball valve. And essentially what it does is it allows beer to go out, but doesn't allow anything to go back in. All right, so it's almost a bit of a one-way valve that's here. Then this section here is where the CO2 comes in, and generally is a one-way valve on here, so which means CO2 can get in, but nothing can go out. So if your gas bottle runs out, then basically the flow stops, but the CO2 doesn't flow out of the keg back into the system. So the beer goes through this the central part. The gas comes through the side here essentially, and then flows through on the outside ring. So if you look at the keg valve or the coupler section that's on the keg itself, so when this ring here pushes down on the black rubber part, it engages the keg valve, which then allows beer to run out through the center ring here and gas to come out the outer ring. And then you have this rubber seal that seals on the outside of that. And that's how it separates. So if you look at the keg itself, here's the keg valve section here. There's a big spear in here. So when you connect your keg up, the CO2 comes through and goes on top of the beer. So the beer level will be here. The CO2 pushes the liquid, so it pushes the liquid down. And what happens is that beer gets pushed up this pipe here, through the center and through the center out. And then it goes through here and then goes to the draft tap. So when the beer keg is fully open, that's when you see the CO2 will push then through here as well. And that's why the keg empties out all the way, because it's got a pipe on the inside that actually goes all the way to the bottom. So let's get into a little bit of background or understanding what's actually happening with CO2. Why is Henry's Law important for both brewers and for barmen, all right, or for the publican even, all right? What you need to understand is that CO2 in beer is temperature and pressure sensitive. And that is explained by Henry's Law. Henry's Law states that at a constant temperature, all right, at a constant temperature, the amount of gas that dissolves in a liquid is directly proportional to the partial pressure of that gas in equilibrium with the liquid. So what that means is that if you've got the same pressure or same temperature and you increase the CO2 pressure, it will result in the increase of dissolved CO2 into the liquid. Okay? In other words, if the beer has been carbonated and it's in equilibrium at a specific temperature and pressure, so if you've got a specific temperature and pressure, only a set amount of CO2 can dissolve in that liquid, all right? And if the temperature and pressure is kept the same, no more CO2 can get into the liquid, no more CO2 can get out, all right? It's in equilibrium. The rate that the CO2 stays in the liquid is then at equilibrium. And that's very important when you are looking at carbonating a beer or when you are dispensing beer. So remember that at a specific temperature, pressure, only a set amount of CO2 can be dissolved in it. So what that means then is if you increase the temperature, all right, to maintain the same amount of CO2 that's dissolved in a liquid, you've also got to increase the pressure, all right? Otherwise, the CO2 is going to either come out of solution, the equilibrium changes, or it's going to go into solution, depending on what you do. And this is going to become a little bit clearer when I show you some of the chart work. All right. The big problem in a brewery is ensuring that equilibrium is reached. You can, in a brewery, in your fermenter or in your bright beer tank, have a specific temperature and pressure, but that doesn't mean that the CO2 level has reached equilibrium yet. It's still taking up maybe some CO2 out of the pressure you're supplying, or it is releasing from the liquid. And that's the biggest thing, why it's important to actually analyze CO2, all right? Because you need to know at what is the CO2 level in there. If you don't have a CO2 analyzer, you're really assuming that the liquid is in equilibrium. And the only way you can do that is with time, all right? Over time, that equilibrium will be reached, all right? But you can't assume if you've just transferred beer in and you've just carbonated that you've actually got the right amount of CO2 by the CO2, by the temperature and pressure that you have. So let's have a look a little bit at an example. So you have different analyzing equipment that you can use. There's Hoffman's portable reading, there's inline systems, there's systems that use infrared that actually measures the change in the infrared absorption through the CO2 level in a container. Or you have these units here, the old technology, right? They're basically made by Zamnagel. And what a Zamnagel does is if you take a sample of beer into a container or, into this, this one analyzes bottles and cans, this one actually from a bright beer tank or from a BBT. What it does is it forces the equilibrium. So if you have a look here, here's one that I've built. This is a demo version. They are available if you want to contact me. And essentially what it does is, if you're taking a sample, it forces the equilibrium so you can then read the temperature and time. There's a specific way that you analyze it. And that's very important, what you need to do for how much CO2 you've actually got in a liquid and how that impacts how you're going to dispense it in draft, in your draft beer. Okay. So Henry is our pal because the law doesn't change. Henry's law doesn't change. So if you have the liquid at an equilibrium and you know what the temperature and pressure is, you can read off what the actual CO2 level is going to be in that liquid. So for a brewer, if you know the temperature and pressure that you're going to be fermenting at, and you know how much CO2 you want, and you can go read off the chart and say, okay, at 15 degrees Celsius, I must set it at 1.5 bar, an example. And that's my spunding will then achieve the amount of CO2 that I require. Henry's law also, if you do any CO2 adjustments, and as long as it's in equilibrium, and you can read off the temperature and pressure, you can go and read, you can determine what the CO2 level is. Henry's law also helps the barman, all right? Because if he gets a keg with a known amount of CO2, so we're assuming here the brewer is giving it to him at a specific pressure, the environment that he's dosing it from, dispensing it from. So if the keg is now at 4 degrees Celsius, and he's gonna be keeping that keg at 4 degrees, and he knows that the amount of CO2 that's in there is 2.4, he can go and read off what pressure does he need to apply to the keg to keep that CO2 in solution so it doesn't break out and create foaming through the system, all right? So there is some stuff that we need to know, that a keg is basically full to the top, all right? So even though you, so if you know and you filled it at let's say 2.4 volumes of CO2, the keg is full to the top, so there's no real headspace in there. So if the temperature goes warmer or colder, it will still be 2.4 volumes of CO2 that's in there. If there's a big headspace, yes, then some of the CO2 can get out of liquid and you can change CO2 concentration. All right, but for this example, let's assume the keg is full. Is it cold or is it warm? The CO2 level stays the same, all right? But because the temperature is different on these, you actually need to apply a different pressure to get the beer out, to not let it foam in line. So let me explain a little bit about that. So Henry's law, as I said to you, he's a bugger. His law does not waver, all right? It doesn't change. So when you change the temperature while you are pouring, you'll change the CO2 stability. As you change the temperature, and if the pressure stays the same, that liquid can't carry or hold that CO2 anymore, and it wants to come out. And if that happens in your line, there's no ways you cannot get this foaming at the tap. It will foam, doesn't matter what. And you need to then change the temperature to actually get the CO2 to stay in solution. Same thing as if you maintain the pressure, if the pressure changes, but your temperature stays the same thing will happen. So if you're dispensing beer out of your keg at 4 degrees Celsius, and let's say your gas gets finished and the pressure starts dropping, all right? Yes, you'll start dispensing slower and slower to the tap, but as the pressure drops and you reach the critical limit where that CO2 cannot stay in solution anymore, you'll get foaming at the tap, all right? If the brewer supplies you the keg, normally, let's assume normally at 2.4 volumes of CO2, but he's got his stuff wrong at the brewery, and it's actually coming in at 2.6 or 2.7 or something like that. If you've previously had a set pressure and temperature to dispense 2.4, the set pressure that you've used previously will not work on this keg. You'll get breakout in the line, all right? There is stuff like keg contamination. So one of the things that I've recently worked on is Saccharomyces diastaticus contamination in a keg. And basically what happens is Saccharomyces diastaticus can actually ferment unfermentable sugars. It actually converts it into sugar and then converts that back into alcohol and CO2, all right? Which means it produces more CO2 in the keg, which means the pressure increases, which means at a specific temperature, that CO2 will then dissolve back into the beer, and thereby totally changing an original pressure that the keg was issued from the brewery, which then means you need to change how much pressure you need to serve that by. And I'll show you an example of that. So let's assume the keg is in a cold room and you're serving it at 4 degrees from your cold room, and you've just got your new delivery and you bring the new keg in and that beer is at ambient. The pressure that you were using there could potentially be too low to get that beer out of the keg and not let it foam. The other thing is also, if you have beer that stays on tap, so as a general rule for me, if you can't sell beer in 5 days from one keg, you technically shouldn't have a draft setup, right? You should be able to move at least 1 keg a week. But if it happens that it stays longer, a half a keg has a big headspace in it, which means there's a lot of CO2. And if the pressure is high enough, it will force CO2 into the keg. It will change the carbonation of the beer, right? Which then means you need more pressure to get it out and not allow it to foam. And I'll show you an example of that as well. So the biggest problem where breakout happens is in this section between here and the cooler. So if the keg comes in, so let's assume it's an under counter setup, the keg is at ambient temperature. When it comes out here, the beer temperature will change. It will go up a bit, all right, because you're now bringing it out here, or if the beer sits here for a while. And as it goes down here, there's slight resistance, so the pressure also goes down. And in Henry's law says, if you change the temperature or the pressure or both, you will change the ability of that liquid to maintain or carry that CO2. So what happens a lot of times is the pressure is set on here, and as it comes out here, CO2 starts breaking out of the keg, all right, in the line. By the time it gets into the cooler to cool that beer down, that CO2 is already out of solution and there's almost no way for it to go back in solution. And then what you will find, doesn't matter once that beer gets in here, once there's a few bubbles of CO2, it will form more and more bubbles will form around it. And what's going to happen here is you're going to get foam coming out here. And it doesn't matter what you do, how you change the back pressure or the flow control valve here, you're going to get foam coming out here. You're going to say, but is the beer's coming out cold? Everything is fine. The problem doesn't exist between this point. The problem exists between here and there. So if you've ever sat and if you have foaming problems and you've just finished pouring the beer and the line is full of beer now, actually sit and watch it. If there's no pouring happening and you actually see bubbles of CO2 coming out of the keg into the line here, and you get a point, you know, the high end of the curve of the draft line, and you actually see bubbles in there, all right? It means that potentially the pressure is too low or the temperature is too high in this line. And that's why it's breaking out. So whenever you have foaming issues at the tap, it's one of the first things that I go and have a look at. So pour your beer, so you have a full line of beer, and then just hold for a minute and actually watch the keg. If bubbles are coming out, the only solution that you can do on that is to increase the pressure slightly, all right? And you can do that in 0.2 bar steps until you see, listen, these bubbles are getting smaller and smaller until there's nothing there. And then you should be able to dispense. But this is a vicious circle because as you increase the pressure, all right, that means the pressure in the keg increases, which means more CO2 goes from the headspace into the beer. And if that keg sits there for 2 or 3 days, you will get this problem forming again. And then you need to increase the pressure again. All right. So the initial CO2 level coming in, the temperature of the keg that you're serving from, all right, and the top pressure that you start off with is incredibly important to make sure this whole system is balanced. Now, if you are at a, let's say you're at an event and you know, listen, this keg is going to last half an hour, and it's going to be done. To prevent any issues, set the top pressure at 2.5 bar, maximum pressure. And then what you'll find is you will have no breakout, no nothing. But you can't do that in a draft setup in a pub because that keg will probably stay there for 2 or 3 days, right? And if you use excessive pressure, that will dissolve into the beer. And then when you serve it, you could potentially get breakout here. But even worse is that when it gets poured in the customer's glass, the carbonation level is very high. The beer is now very spritzy. And it's a mouthfeel change for the customer and also a flavor change for the customer. And that was not the intention of the brewer when he released this keg to you, let's say at 2.2 or 2.4, whatever. He released it at the pressure required, at the CO2 level required that must go into the glass. So let's have a look at this. So this is an app that you can download. It's called McDantum, all right? And essentially, it allows you to see, if I use blended gas, pure CO2, you know, what kind of pressures is required, all right, to dispense this beer. So let's have a look at this example here. This keg is at 4.4 degrees Celsius. The altitude needs to be taken in consideration because we're quite high up here in Johannesburg. Yeah, alcohol content is there. If you set the keg, if the keg comes to you and it's at 2.4 volumes, the minimum pressure you require not to have issues is 0.96 bar to dispense it at, right? That same keg, right? So this same keg, if it's at 2.4 volumes, but the keg is sitting at 21 degrees Celsius, to dispense it and not have issues, you need to almost dispense it at 2.27 bar. You see the difference, how temperature has an impact to keep the CO2 level the same. So if you now apply the same rule, all right, on a 4.4 degrees Celsius keg, at 2.27. That 2.27 at 4.4 degrees Celsius can carry up to 4.12 volumes of CO2 before it will start breaking out. But if you have got this keg and it's sitting with 2.27 bar for a week, all right, what's going to happen is that headspace is going to make some of that beer, some of that CO2 dissolve into the liquid. So it's going to change it from 2.4 and increase the CO2 level. Because remember, beer wants to be at equilibrium at a specific pressure and temperature. And what's going to happen over time, the CO2 is going to come up and then it's going to give you pouring issues again. So if you are, if you've got a cold room, the keg in use and the standby keg is got to be at the same temperature when you're actually going to be pouring them. Because think about this now. If this requires 0.96 to pour at 2.4 volume CO2 at 4 degrees, if you bring in a warm keg into your cold room and you put the same conditions onto it, my regulator is set at 0.96, that 0.96, all right, will not be able to maintain that CO2 in solution. So if you apply that with that temperature, the CO2 will break out as it's coming through the line on the way to its chiller, and you're going to get foaming. So whenever you use this kind of setup where you've got minimum pressure set up, say 1 bar or 1.2 bar for a cold keg, the standby keg's also going to be at the same temperature. You can't just bring it in. Otherwise, you're going to have initial issues when you bring in the new keg and you're pouring until you can have this thing at the same pressure. And what's going to happen? Somebody is going to up the pressure, yeah, because it's pouring wild, and it's going to be left at the higher pressure, which means as the keg cools down to 4.4 degrees Celsius, CO2 in the headspace will dissolve into the beer, and thereby changing the carbonation and thereby changing the mouthfeel and the flavor impact for the customer in there. All right. So do you guys see the temperature and pressure required, all right, to perfectly pour a 2.4 volume beer is very, very different. So let's have a look. Let me just go to the next one. So here's the same example again. Whoops. There's the same example again. The keg is at 4.4 degrees Celsius. The pressure is set at 0.96 to dispense it. That carries the 2.4. All right. There's the previous example, all right, of 4.4, 2.27, and this is using pure CO2. What's going to happen? That keg's going to carbonate. But sometimes when you've got a long line, you've got a lot of pressure drops, and you actually require increased pressure to push the beer all the way to the front. And then what you can do is you can use partial pressure to help you. So if you then use blended CO2, all right, and this one is 60% CO2, 40% nitrogen, all right, you can use the same pressure, 2.27 as what you did, and it will still maintain 2.4 volumes of CO2. Because remember, let me just go back here. If you look at Henry's law, one of the things it states here, Henry's law states that a constant temperature, the amount of gas that dissolves in a liquid is directly proportional to the partial pressure of that gas in equilibrium. Now, normally when you dispense with 100% CO2, it doesn't matter, there's no partial pressure. But when you're dispensing with mixed gas, so say nitrogen and carbon dioxide, so sure mix 60, right? That means only 60% of the pressure of that gas is CO2, right? So that means the actual impact of CO2 pressure on the liquid is roughly only about, what's that, 1.2 bar, all right? So that's not going to change. Whoops, hold on. That's not going to change the CO2 volume. So even though this is at 2.27, the beer is actually only experiencing roughly about 1.2 bar of CO2 pressure, all right? Which is not going to change the CO2 level, all right, in the beer. And thereby allowing you to use higher pressures to dispense beer without it affecting the draft dispense. Now, so I think generally for most small breweries and tap rooms, they use CO2 dispense gas, then this rule will work. But if you're using a cold room, it's far away and you've got to push that beer all the way to the front taps, then typically consider mixed gas, all right? And the reason why mixed gas works is that you can go increase pressure, but because there's a smaller portion of CO2, it means that there's a smaller impact on CO2 dissolving in the liquid. So that's the McDantum app. You can download it if you want to see. So for brewers, after a beer has been kegged and it's been standing for a few days, you can use Henry's Law as well to actually see what's the actual CO2 in your keg, all right? Because there's almost no headspace in a full keg, all right? As long as you know what the temperature is of the beer in the keg, right? So maybe a glass of water in the cold room with a thermometer in it overnight. And this requires that you must know the temperature and the beer must be in equilibrium. So if you've just kegged it, I don't think you can use Henry's Law to get a quick answer from it. You'll probably have to wait a day or so or 2 days in the cold room. And then you can just do you've got this little keg filler that's got a pressure gauge on it on this side and valves here that you can close it off and you can close off here. Or you can build your own little unit. Yeah, these are a little release valve there, a gauge, and these are just using John Guest fittings, right? If you now go close the liquid port, close the gas off here so you don't have any gas escaping, and you put this coupler on the keg and you actually measure the internal pressure. You know the temperature and you know the pressure, you can go read off the chart what is the actual CO2 of the liquid. And you can then tell the public, and listen, this is probably about 2.4, 2.5, whatever the CO2 level is. And there's an app for you as well that you can use. It's called a keg carbonation calculator and chart, all right? And essentially you can type in the CO2 volumes and the temperature and it will tell you what do you need to set the regulator at. One thing that you've just got to remember, if you're using this app, it doesn't compensate for level above sea level. So these charts are all done at sea level. So if you're here in Gauteng, you probably need to add about 0.2 bar to this number, all right? So what this means is, if you have a keg, all right, and you can maintain the temperature at 2 degrees Celsius, and you want 2.4 volumes, all right? And let's say you're at sea level here, and you set the regulator at 0.62, all right? And you can take that keg, put it in, let's say, a paint shaker, and you can control the temperature, and you can constantly feed pressure at 0.62 bar. You can shake that thing for a week. You will not dissolve more than 2.4 volumes of CO2 in there. Because at this temperature and at that pressure at sea level, that is the equilibrium CO2 amount that will dissolve into the beer, into the keg, all right? You will not be able to get more than that. So even for homebrewers, or, you know, if you are shaking and you're force carbing your keg, you set it at that and you're shaking it and you can control the temperature to be consistent, you will achieve that kind of volumes. Now, obviously, the closer you get to equilibrium, the slower that equilibrium will happen. So what I always recommend is if I'm force carbing and I'm doing it manually, I go another 0.2 on top of that and force carb it, then using that. Here's the chart. It looks something like this. So if you go, Henry's Law basically exploits this. So if you know the temperature and you know that the liquid is in equilibrium, all right? So let's assume at 0 degrees Celsius. If it's at equilibrium, if you're reading a 0.55 bar pressure, that means the liquid inside is at equilibrium will be 2.48. So then you'll know what you can tell the publican what he's getting. Because remember, he's getting a full keg. There's no ways that more CO2 can actually get into the headspace. So it's actually maintained, that CO2 level is maintained. When he dispenses it, so say if he dispenses it at 4.4 degrees Celsius, all right, we were at 0.55, what were we at? 2.48. So if he's dispensing at 4 degrees, 2.48, so it's roughly, yeah, that means he needs to have 0.83 to maintain that 2.48 that's dissolved in the keg. If you go more CO2, it means CO2 will go from the headspace into the keg and change the carbonation. All right, so if you are doing it at 4.4, yeah, that means that at 0.9 bar or whatever, you'll change the equilibrium and the beer will slowly but surely carbonate. If you try and dispense that at 0.55 at this temperature, 4.4, that beer can't hold that liquid and the CO2 is going to come out of solution and give you issues at the tap. All right. So before I step off this is a lot of information. But if you understand the Henry's law, at a specific pressure and a specific temperature, only a certain amount of CO2 can be carried by the liquid. And if you change any one of those, it's either going to absorb more or it's going to lose it out of that liquid. And if it loses it out of the liquid in your draft tap setup, you're going to get foam at the tap. All right. If you increase the pressure a lot and keep the temperature the same, you're not going to have any issues with foaming in the tap because the liquid can carry it at the higher pressure, but you're going to get more and more CO2 dissolving into the liquid. And eventually you're going to reach the point where the new equilibrium is set and you might get foaming again then. But in the meanwhile, the customer is getting a glass of very carbonated beer. And when you're pouring it in the glass, you know, it's foaming quite a bit in the glass.
Danie, we've just got one question here quickly. If you're keeping your kegs at an ambient temperature and dispensing through a chiller, how do you decide what to set your serving pressure at? Since the ambient temperature will obviously fluctuate over time.
Yes. So if you have that kind of setup, you've got to, you're going to have issues. All right. But you can manage it. All right. If you know that, listen, this keg is going to be on here for a long time, you need to look at your pressures on a regular basis. If you start getting foaming at the tap, you need to increase the pressure by 0.2 bar. Knowing that with time, you're going to dissolve more and more and more beer. So if the keg is on there for a long time, you know, you almost need to degas it after a certain period of time. But if you look at this, yeah, so if that keg is at ambient, you probably need that kind of pressure to get it out of the keg and to the chiller, all right? Because this is the part that's the problem, all right? Once it's in here, you're changing the temperature, all right? Yes, there is a bit of a pressure drop because the beer goes through a cooling coil and all of that, but this temperature is a huge impact to stabilize the amount of CO2 that liquid can carry. So as long as you can set the pressure, all right, to not have breakout in this section, once it gets in here, the temperature is going to nullify any issues that you might have. So this is the part, if you have a setup under the bar and the beer gets warm or whatever, and you're having foaming issues here, this is the first part I would have a look at. If you don't have CO2 breaking out here at all until the chiller, there must be another issue why you're getting CO2 breaking out here. But if you are serving and you can see CO2 bubbles coming out here slowly, right? You know that the pressure is too low. And even if the temperature can cure all your ills, if the CO2 has come out here in bubbles, you're buggered. It's not going to go back in. And as it goes through here, it collects more and more CO2 out of the solution, right? And by the time it gets here, it's just going to come out as foam or very, very foamy beer. All right. But because this keg is warmer, all right, is sitting at 21C, to keep 2.4 volumes of CO2 in solution, you can go a higher pressure. All right. Now, this thing is, I wouldn't go above 3 bar. So if you've got keg troubles and you say, listen, I'm going to up my pressure by 2.2 bar, pour a pint, see is it getting better? All right. No, it's not up another 0.2 bar. I think once you get to 3 bar, you've got the limits, a safety limit that you need to consider. I wouldn't go above that. All right. So if you need 3 bar to dispense the beer and it's still foaming and it's still breaking out as it's coming out of the keg, you unfortunately probably need to degas the keg a bit. So what you need to do is you need to drop the pressure in the keg. So take the keg off the system. All right. Let's go here. You can take it off the system, close all these valves, drop all the pressure, the temperature, so let's say it's 21 degrees C, and then you shake the keg. And what you are doing is you are reforming a new equilibrium. Because right now, when you shake the keg, that CO2 cannot stay in solution. It comes out, it goes into the headspace, and you'll see the pressure will actually start increasing as you're shaking it. Because you can shake it and it will keep releasing CO2 until it gets to its new equilibrium point. All right. Once you've shaken it and you've released the pressure, and you can shake it until it doesn't release any more pressure above 2.27 in this example. Sorry, that's the wrong example. If the keg temperature is still 21 degrees C, you keep shaking it and it releases pressure up to 3 bar, and you keep releasing pressure. And then you keep shaking it and it doesn't go above that, you know you've reached the equilibrium point again. And then you can connect it back up to the system, up the pressure to 2.4, 2.5, and it should pour again normally. Does that answer that question?
It does. Thank you, Danie.
All right. Now, there's some other issues that, that also plays in a draft system. But in my mind, almost a lot of the issues I've seen is related to Henry's Law and what the brewer has given the publican, and then also the temperatures at the publican or the pressure that the publican uses to dispense it. And as long as you know Henry's Law plays a huge role, you can do that basic problem solving. That is, when you've poured a beer and there's bubbles coming out of the keg, you know the pressure is too low. The liquid can't carry the CO2 that's in it, and you need to increase the pressure. There's a safety limit, how far you can do that, all right? And if you reach 3 bar and you've put a new keg on and it's still breaking out, you've got to ask the question, what's going on in the keg? There might be something else, a Saccharomyces diastaticus or something else that's produced more CO2, or the brewer gave it to you at an incorrect CO2 level. But there is other issues. Beer line. If you kink a beer line, right, you're basically creating eddies in the line, and essentially you can get CO2 breaking out from that because you've got now agitation that also gives you issues. And if you're close to the limit where your Henry's Law just allows you the CO2 to carry out, and now you have a kink in the line, all right, it forces that CO2 out. And once the CO2 is broken out in line, it's going to get foaming at the tap. You can't redissolve it. So whenever there's a kink line or something like that, replace it. All right. So have a look. If you don't see CO2 coming out of the keg when you're pouring, go follow the line. See, is the beer line actually kinked somewhere? Is there something that's happened that somebody put something on a line or whatever? Keg valve damage. I've seen this a few times of late, and I haven't seen that in a couple of years, which has been very odd. Is when the actual spear is damaged and it's allowing CO2 to leak into the product line where the beer comes in. And I've seen that a few times, and that's generally, you need to send that keg back. You can't do anything with it, and put a big sticker on it or mark it so that the brewer actually replaces that spear. There's potentially an issue on there. One of the other things is sometimes when the guys do CIP, they switch off the keg chiller and the ice bank falls away. And then, the beer temperature actually doesn't go down as low as you think it is in a chiller, and you get CO2 breakout that happens in there. So just always keep an eye on it. If the guys have been there to clean the lines, whatever, make sure they switch on the chiller again that is in there. Or if you're using a cold plate, if the ice starts running out, the beer starts pouring while it starts foaming. Why is that? Henry's Law. You're changing the temperature, but you're keeping the pressure the same. and thereby changing the solubility of the CO2 in the beer, and it breaks out. So there you go. Henry's law applied in a cold plate chiller.
Only another quick question. When degassing the keg, and there's a lot of foam coming out the keg, do you just let it foam out into a jug, or what should be done?
So generally, if I'm going to degas and the keg is quite full, it's very easy when the keg is half and it's giving you issues, because then the foam doesn't really go up that far. But if it's full, unfortunately, you're either going to have one, product loss in the sense that it comes out, all right, or two, you're going to do it over a couple of hours. You got to do it now, put it on one side, drop the pressure, shake it a bit, let it settle. 2-3 hours later, do it again. 2-3 hours later, do it again. Or take a liter of beer out of the keg and unfortunately waste it. And this is why it's so important that your setup of your draft is done correctly, that you apply the pressures correctly, understanding Henry's law. Otherwise, this is going to be a constant issue that's going to happening. If your system is set up correctly and suddenly the new kegs come in and give you issues, you must tell the brewer and say, listen, what's changed here? What is actually going on there? So yeah, if the keg is full, unfortunately, you either got to drain some liquid out and do it, or do it over time, or let this foam come out, unfortunately. So if you're in that situation, you unfortunately bug it already. So you want to stop the system that happening. Otherwise, it's going to cost you money in the sense of losses.
Another question there, Danie. How do we work out the volumes or grams per liter? I know my carbonation temperature, pressure, and time, or do we just get an app?
All right. Just how are you carbonating? Are you using a carb stone? Are you force carbonating? Are you just doing CO2 in the bottom of a vessel, or are you doing force carbing like in a keg? What is the background to that question? What are you doing with your beer?
Okay, Russ, I'm going to unmute you quickly so you can ask Danie the question quickly. Give me a second, let me find you here. There you go.
Hi there, sorry guys. Yeah, we're doing forced carbonation, 100% CO2.
100% CO2. Okay. And your forced carbonation, is it with a carb stone or inline or in a keg shaking, or how are you doing it?
Yeah, we do it through the coupler in the keg.
All right. So then what you need to then do is follow this rule. So take the carbonation calculator. All right. Work out what volumes of CO2 do you want in the beer. If it's 2.2, 2.4. So if the keg has had an overnight time to cool down, you buy a glass of water or something in the cold room, or a jug of water, so you can actually check the temperature. If you know that, you can then work out what is the pressure required. Because if you shake that keg, all right, and you've gone this pressure, it will not carb beyond that. All right, it will not. There's no ways. Henry's law doesn't allow it to happen. All right, so you'll have to work out what volume do I want. So even if tomorrow, if the temperature is 4 degrees, you type it into the calculator, it will give you the new pressure that you need to set the regulator at, and then you are carbing it. The problem with carbing a full keg is you've got very little headspace in there. All right, so it takes very long. So you're either going to be under carb because you think, as I've shaken this keg now, there's so little headspace for the beer to mix with the CO2 and then dissolve in all the time, that you're probably going to undercarb, or you must leave the keg on pressure for a set amount of time. All right. So if you want to do this quickly, you can up the pressure, but then you have to work out how long does 3 bar take on top of a keg to give me the right pressure. All right. After the right volumes of CO2. That's going to be a trial and error thing that you're going to do. So you're going to almost have to put the pressure on top of the keg, leave it at the cold room, and allow it to naturally just carb every day. And then what I would recommend is you take the keg off, let it stand for a day, maybe shake the keg, and then tomorrow you take your little pressure sense, this one, you put it on, you know what the temperature of the beer is, you'll read the pressure that it gives you, because even if you put the keg in there at 3 bar, overnight it will absorb that CO2 and it will tell you, it'll only absorb that CO2 up to the point where it's reached equilibrium. And then you can say, okay, this is the value that I've got. So that's the problem with in-keg carbonation, is because your headspace is so small, it's very difficult to do it. For my home system, I actually have like an old exercise shaker machine that I've converted. So I strap the keg onto that and I set it to 20 minutes. I set my pressure to what I've worked it out to be. And I carb at 16 degrees, doesn't matter. I just know that I've got to set the pressure at this, and then I let it run for 20 minutes. And then it's carb to the right level. Because once it gets to the temperature and the pressure that CO2 can carry, it will not dissolve anymore.
Another one here. Does transportation of kegs from one place to another have impact on the change of CO2 levels?
If the keg is full, all right, the CO2, there's no headspace for the CO2 to go into. So the keg is sealed. It will not change the amount of CO2 that's dissolved in the liquid. But the CO2 has now been agitated in this keg. So if you take it off immediately, put it on, you potentially will have to put a little bit more pressure on there to just stabilize that CO2 coming out. If the keg is half, so say you come back from an event, all right, and you've had low pressures or whatever, and generally from an event, you've set the pressure to 2.5 bar, the keg is half, you take it home, it's got the chance now in the car to actually shake and dissolve the CO2 from the headspace in. And then when you get home, it actually pours very wildly, because now you've actually increased the CO2 level in the beer, and it's now very carbonated because of that. So that's a big issue. If you go to events, you know, before you actually leave the event, use that little tool. You know that, listen, roughly at this temperature, I always set, so when I dispense at home, I dispense at say 2.5 bar, because I don't want any issues with anyone can pour it in. And then at the end of the evening, before I disconnect all the kegs, I take my unit out and, okay, so roughly at 4 degrees, it's dispensing, set the pressure all the way back to 0.8 bar, release it, put it back in the cold room, and tomorrow there's no, it hasn't had chance to absorb that CO2 that's in the headspace. Does that answer the question?
Perfect, thanks, Danie.
So yeah, physical inline obstruction. I've seen this a few times, and I don't think it's a major issue for craft brewers. But if you're using a plastic cap that goes over the top of the keg, you know, that anti-tamper proof thing, sometimes when that comes off, you know, the barman pulls it off, a little plastic piece breaks off from the clips, the safety clips. And if the guy doesn't see that there's a little piece there, and he puts the coupler on and it gets sucked into the coupler, that little plastic can't go past the little ball that's there, or that torpedo, and it gets stuck there. And you actually get then, as the beer comes out, it's agitated through that process and it breaks out. It doesn't matter what you do with the pressure then, it actually gives you issues. So sometimes if you've changed the pressures and nothing changed, take the coupler off, have a look inside. Is the ball loose inside? Is everything okay? You know, I've seen kitchens that's got chips and you name it all over the kegs, and you know, it looks rough. If that coupler, that sealing surface hasn't been cleaned properly, something can get stuck in there. So I have seen physical inline obstructions. Beer line that's dirty. Over time, beer stone gets formed in the beer lines, and it creates nucleation points where, if you're just slightly off on the on Henry's law, you know, you're getting close to the point where it's sensitive, it will actually form a nucleation point. Like if you think about in your glass, and the guys that etch the glass at the bottom, like Castle Lager and all these guys do the etching in the bottom of the glass. You actually have CO2 breaking out constantly from that. And that requires you to do a good acid clean of the system, especially if your line is quite old, kind of you're getting up to 2-3 years that it goes in there. But generally, beer lines, the cleaner they are, the less issues you have as well. Never mind flavor impacts and those kind of things. The other thing is tap blockage. Either fully blocked or partially blocked, and you create a flow disturbance there. Especially if you've got high IPAs, those kind of things, and you have that hop material actually sitting at the flow control bar that's there, and it actually gets stuck in there. You can actually get, also if you have high yeast loads and those kind of things, the tap needs to be taken apart and cleaned on a regular basis. So that could potentially also be an issue. So if you're doing IPAs and that tap is pouring wildly, and you know that, listen, I've done like a bucket load of hops in the fermenter, it might have been some carryover. The tap blocks or partially blocks and gives flow issues in there. Contamination, I've spoken about. Your keg goes to the publican. It's in your cold room. It gets there. It gets stored out in outside maybe, or in a back room or something, and it sits there for a week or two. If you've got Saccharomyces diastaticus in there, that can produce more CO2, and it changes the carbonation level and then gives issues when I try and connect it up. So that could come from that. Poor cleaning, as I said, the lines, and then dipping the tap spout. That essentially acetic acid contamination can get into the lines. So there's no reason for your beer, as you're pouring it in glass, for the tap spout to touch the beer. Yes, hold the glass at 45 degrees Celsius or even more if you need to, but it should never touch the tap spout. So good practice is to either a water spray at the end of the evening when you can close down, or maybe a sanitizer to spray the tap spout. You get these plugs that you can put in, you can use that. That also gives you some flavor protection. It's not really a CO2 thing, but more acetic acid contamination issue. Then, one of my big issues that I've got, and the guys that are on Hopaholics know, it's one of my pet peeves, all right? Clean glasses. So let's assume you've spent all this money to put in mixed gas, you've got state-of-the-art chilling, the brewer's done his job correctly, whatever, and it's pouring perfectly in a pint. Why do you serve it in a dirty glass? You must, if you're going to serve beer in a beer glass, remember that liquid is super saturated with CO2, right? It's come from, you've now pushed it through a tap that's poured it carefully so that minimal CO2 escapes. That's why you have foam on top. There is CO2 that's escaping, all right? That CO2 wants to get out all the time. And if the glass is dirty, all right, it's going to do two things. It's going to stick on the side of the glass, all right? The CO2 is going to stick on the dirt, or you're going to affect the foam head that's going to form in here. And there's nothing as good as a clean glass that is brilliant with the beer that's in it, and a nice, thick, fluffy foam head that's on top there. And you think, oh, yeah, this doesn't happen often. Listen, it happens a lot. This is a pack shot. So if you've got a company that's going to take photos for your menu or something like that, make sure they use a clean glass. All right. I've seen so many promotional material with a dirty glass. See how the CO2 sticks on there. The glass is clean. There's nothing for the CO2 to stick on. They will not be on the side of the glass. All right. Yeah. So have a look at this. This is a picture Stefan sent me. Look at that. Do you notice the difference in the structure of the foam bubbles here? You see how big these bubbles are. And that's called coalescence. And I'll show you a little bit more on coalescence. And I can almost guarantee this glass laid on its side in half a tub of water somewhere. And that dirt that's on here is basically from a glass not being washed properly. The rest of the glass might be clear in there. If a glass looks like this, it's dirty, right? There's something that's gone in there. Either somebody's wiped it with a dirty cloth or left fibers on the inside, or it hasn't been washed properly. But have a look at how a dirty glass changes the perception in the foam head as well, especially if it's got fatty material in it. So if you've got a glass washer, make sure all the chemicals that go in there is correct. Wash the glasses separate from the plates if you're in a kitchen, or use a brush washer in there. I want to get the shits if I see this, if I'm served this. And as a general rule, I send it back as a general. I'm not going to pay 45 Rand for a beer and you're going to serve it to me in a dirty glass like this. So it happens a lot. Right? Another promotional shot. Look at that. This is probably a wipe from a cloth or something in there. So see, look at the change in the foam structure that actually happens. Can you guys see my pointer? Julian?
No, loud and clear, Danie. You can see it, yes.
Okay, cool. So you see how different it is. And this is because of what they call coalescence. It's because you actually physically changing this bubble membrane of the product. You're actually breaking it down. So coalescence is the merger of two bubbles. So it's the rupture of the film between the bubbles, and it produces larger, less stable bubbles. So if you've got beer poured into a glass, you want those bubbles to be as small as possible. They're very stable. They give a nice foam head on it, and it looks fantastic when you present it to the client. So in a perfect clean glass, coalescence is not an issue. You don't get this thing. But if a glass has got some lipids in it, oily snacks, if the client has been eating chips or oily snacks, that's his problem. But when it gets to the table and somebody else's oily snacks from the previous use is still on there, that's a problem. Cleaning agent, dirty glasses leads to what they call catastrophic coalescence, and thus the loss of foam stability. And essentially, if you have a look at this, what happens is there's two things. You either have the hydrophobic particle, or you have a spreading particle. And if you look at the bubbles, where they're touching, these particles actually allow these two bubbles to become one, and the bubble becomes bigger. And so when it's been poured, you can pour it with a perfect head, but almost immediately you see this happening, where the foam head falls away and you get these huge, big bubbles. It's not a uniform shape that is in there, right? And the only way to get rid of that is to use a glass washer. If you are a smaller brewery, invest in one of these things. Here's the Sputnik. It's a budget version of the Spoelboy. The Spoelboy can be quite expensive, but both of these has got a center brush that goes into the glass. It's got the soap in there, and then it's got the brushes on the outside, and you can move the glass up and down, turn the glass and clean it. And then when you push it onto here, it's got clean water spray, and essentially then it's ready. So when it comes out there, you can give it back to the customer. You can you serve the beer. If you're gonna let the glass dry, put it on a drying rack. Don't put it straight onto a rubber surface or a metal surface that seals the sealing. Otherwise, you're gonna get this like steaming effect or condensation effect in the glass. You got to raise the glass, dry it with air, but don't wipe it on the inside dry. For a restaurant, something like this is more a home use. One of the home brewers actually sent me a picture of this. This is great for that kind of stuff. But I mean, again, you can't put this in a basin where you've just washed plates and then try and think you're going to wash clean a glass on there. All right. So it's one of my big things is it's a whole package. All right. The brewer must keep the keg to you correctly. You must have the correct setup to dispense the beer and then give it in a clean glass. and you have this overall package that gives the customer this fantastic beer, great aromas that come off it, drinks fantastically, and he's not gonna worry about paying 45 Rand for a beer. But if that beer arrives at him and it looks like this, that is a problem. So it's, I think for draft setup, glass washing is an integral part of a draft tap setup. Let's quickly look at cleaning. I think some of the first things is obviously you're going to be working with caustic or cleaning material. Got to use some rubber gloves, eye protection, and CIP and progress signs. There was a big court case in the US where the guys were busy cleaning the kegs at the back, right? The barman came in and somebody asked for a beer. He didn't know that the guy cleaning the lines were at the back. He's connected up the keg cleaner, and so this barman poured a mixture of beer and caustic and gave it to the client. The client swigged it down and got chemical burns from it. So when you're going to be CIPing the system, mark it off. Don't just tell the barman, because they swap over. If you only have one barman, yes, you can probably do it. Put glasses on the system or whatever. Take note of that as a risk for CIP. All right, minimum cleaning for a keg line is 2 weekly. However, if you do unfiltered beer, stuff with high loads like IPAs, those kind of things, you probably need to look at doing it more often than that. But a filtered beer, that kind of stuff, you can probably get away with 2 weekly minimum on there. There's no reason to go longer. All right. Caustic, strong, 2 to 3%. Basic rules: flush out the beer with water, push the caustic for initial clean. You know, when you put the caustic through, you get that initial yellow brownish liquid coming out, and then it's clear. Clean and dismantle the taps. You have to dismantle the taps. And if you've got 4 or 5 taps, don't take all the taps, put them in one bucket and all the parts in one bucket. You're going to pick up issues where the valve sticks and those kind of things. Each valve, clean them separately, put them together as one unit again. I don't know, they're supposed to be identical, but I've seen that a few times now, that you pick up issues of the tap then afterwards when you swap barrels between taps. So once the tap's clean, fill the caustic. If you use pump circulations, and I haven't seen many of these in South Africa, maybe the bigger outlets, but most craft guys use, you know, like a CIP keg or something like that. Push and soak 20 minutes is what you require. And I know this doesn't happen. You know, people are under pressure, those kind of things. It's push through, done. If you do it on a regular basis, maybe, yeah, you can get away with doing it shorter time. But this is the recommended time that you need to do it. Acid clean, and that's essentially for the beer stone. Once every 3 months, you do an acid clean on it. And if you're a brewery, chase a quick sanitizer through it for sure. Go for it. If you, you know, if this is an issue for you, you can buy this. There's a product called Dasana Max, and they actually have a color changing technology in them. So when you are, when the thing is dirty, as soon as it goes clean, it changes color, and then that way you know, listen, I've cleaned the line properly. And then, but they are quite pricey. But you know, for a brewer, if you've got all the stuff, you might as well do it this way. But you know, there is this option that you can go as well. Things that you have to do: dismantle the tap and soak and clean at least 2 weekly. The coupler, a coupler never sees any love. And in my opinion, get a bucket with a little bit of cleaning liquid in a brush, and you can just scrub it. They do say dismantle it, but I think if you're not comfortable, you know, with doing it, rather just soak the coupler and give it a good clean, and then spray the sanitizer and then connect it up. And then there's quite a few guys that are starting to use fob detectors. I don't know if you've gone into some cold rooms and the fob detector looks like it's growing its own life on the inside, you know, lots of little colonies. And it's generally yeast, especially if you doing unfiltered beers. Those things, you can clean them in line. a 2-weekly basis, but you'll have to take them apart every 3 weeks. Otherwise, they're going to become a point of contamination. Yes, and that is my my talk. If you guys are interested in that little CO2 analyzer of mine, you can give me a contact. I can help you guys on there, or if you've got some issues that you need some problem solving on, please feel free, give me a shout. Let me see if I can assist on that front. Julian, back to you. Questions?
Excellent, Danie. Thank you very much once again. It was very good as usual, and obviously we've learned a lot once again about obviously carbonation and serving in clean glass. I am going to allow people, if they want to unmute themselves to ask any questions. I don't see any more questions on the chat line. Is there anybody that has a question? You can raise your hand and unmute yourself. Anything else from anybody? Nothing. Amazing.
And
right, everybody. Well, that concludes today's webinar. We hope you've enjoyed it. If you do have any other questions, obviously you have got Danie's email address that he just showed. It was danie@beardedbrew.co.za. He obviously consults on a regular basis, and he's got some really cool devices that he has built and developed over a period of time to help with obviously the carbonation and checking carbonation of beer. And then obviously you mentioned the different cleaning things like the Spielboy or the Sputnik. And yes, it is definitely a good investment. We use it in our brewing as well, especially when we're doing beer judging and tasting. It is quick, efficient, and a clean way to do it. He did mention that the Spielboy is expensive. It is about the price of a dishwasher, but it cleans it much more quicker and more effectively than the dishwasher will do as well. We swear by it, and we've had one, actually got one at home as well, and it's very still.
Yeah,
So,
I think
Danie, anything else from your side?
Yeah, I think those Spielboys or the Sputnik, those units allows you to wash, so especially if you've got lots of glasses, because it replaces the washing water and rinses with clean water all the time. It's not like that the brush section actually gets dirty with filthy water. That water gets every time you flush, it actually puts a little bit of clean water into the washing.
Recycles it, yeah. So you got to keep on putting detergent in as well as you go along.
Yeah, you got to put a bit of detergent. But I mean, you can literally wash a glass in 15 seconds flat to draft quality cleanliness.
That's it. Awesome. Quick one, Sean. Lucky here. Just wondering how altitude affects carbonation levels.
All right. So if you remember in the presentation specifically, in that McDantum thing, there was a altitude correction factor. And essentially, when you're carbing, if you're using the equilibrium chart, you need to remember that it was set up at sea level. So if you come up to Gauteng, they say, if I remember correctly now, it's every 2,000 feet, you need to add 0.1, all right? 0.1 bar to that chart to do that. So if you're carbing the keg here in Johannesburg or in Cape Town or Durban, you just need to take that in consideration. If you want to carb it to the correct level, you need to just read it off the equilibrium chart with that change. But 1 gram of CO2 dissolved in a liter of liquid here is the same as 1 gram of CO2 dissolved down that side. It has to do with the actual measuring the CO2 that changes with altitude.
Excellent. Thank you. And on that note, everybody, we wish you happy brewing, happy pouring, obviously happy cleaning, and wish you well for the rest of the week. Have a good weekend ahead, everybody. Take care, stay safe, and we'll see you on the next one. All the best. Goodbye.